important video because this week we're talking about the circuit simulator of choice that we're using for the rest of this course. Personally, I would prefer that we didn't have to rely on a circuit simulator, but as we're forced to an online environment, we have to do something. I would prefer you to have hands-on experience with breadboards, even soldering and playing around with components to see how they physically work, but we are forced into a situation where we have to use a simulator. So let me tell you about the one that I've chosen for the duration of this course and probably for next term since we'll be online there as well. Um, my requirements are pretty much this. I wanted a low learning curve since I won't be able to physically be there to support you and help you. So it's easy to jump into. Definitely free. As I've explained before, I try to make everything in this course uh, zero cost to the student. That means ZTCs of zero cost textbooks as well. And I also wanted something that would demonstrate the physical processes that are going on within the circuit so that you can have an intuitive understanding of what's going on. Enter circuit simulation. Here we go. So the one that I ended up choosing was one that I haven't heard of before until I started looking right before this class was launching, and it's called simply Circuit Simulator. We're working on version 2.2.9 by a gentleman named Paul Falstead. So we're going to talk about getting started, how we can jump in, we're going to tour some of the concepts of the simulator. We're going to start really simple, very foundational in this video, and we're going to build as we go over the course of the semester. We'll talk about how we lay down some parts and components, and then we'll build a circuit together so that you can see it's the real deal. All right, Introduction to Circuit Simulator. I love the name. Leaves nothing to the imagination. That's fantastic. It was originally written, as I said, by John Falstad, and it was written in Java. It was then ported to JavaScript, which I've did some research, and again, it was ported into a desktop environment through the Electron.js framework, which I have some experience with, so I'm really happy about hearing that, and that's super cool. I've added 3 links to this slide. One is for the online platform Circuit Simulator on John Falstad's website. Another one is the same simulator but in full screen mode. And then another one to download an offline version that you can use Windows, Mac, and Linux. So you should be covered at all bases. The only thing that I can't see the offline mode working on would be, we'll say, a Chrome laptop, a Chromebook, but you also have the online version for that, so it shouldn't be an issue. So let's take a look. It's actually a pretty simple interface, which is going back to the first tenet. I wanted something that you could jump into quickly, that wasn't overwhelming. It might be a little feature light, but I think it will do exactly what we need it to for this semester. And if we need to progress into something that's a little more intense, we can do that and we can investigate those avenues. But I think for 101, we should be solid. So instead of going through all of these in the slide, I'm actually going to pull up the simulator so we can talk about what our interface looks like. Let me grab this really quickly. And here we go. Okay, so like I said, it's a little sparse at first glance, but it has all the functionality and features that we need. The things that I really want you to pay attention to is obviously this big main screen right here. This is going to be where our circuit diagram is going to be drawn. Everything that we do when we're starting to draw components is going to be from this menu right here, which is Draw, aptly named. When I'm asking you for assignments, you will be drawing your circuits using the features and components in the draw command, and then you will be exporting them, exporting as text, and then you will be uploading those text files to Canvas, and that's how I'll check out your circuit. Pretty simple. See, so we've got the draw command, which allows us to add components, as we said. Another important facet would be this area right here. This is how we run, stop, and reset our simulation. We can also change the speed at which the simulation is happening and progressing, which is extremely helpful. This section right here, we'll talk about a little bit later, is important because it talks about some of the specifications that are currently going on in our circuit, specifically runtime, how long it's been running for, and also if we have any bad connections or errors in our circuit. And it's a surefire way to save yourself a lot of head scratching and figure out where you went wrong. The only other thing that I think might be of interest to you later on is this section called circuits is a fantastic layout of pre-built complex circuits that you might want to use in some of your advanced projects. I don't think anything we'll be doing in 101 will pertain to this. We'll probably build them from scratch. Um, but there's all kinds of great filters, diodes, 555 timers, fantastic, really good, more advanced stuff, but it's all there. Let's jump back into the PowerPoint, see if there's anything I missed. Oh, I did miss something. There's also a built-in oscilloscope feature, and we haven't really talked about oscopes before, but oscilloscopes allow you to visually see a representation of voltage, current, resistance in a circuit. And had we been in class, we have actual functioning physical oscilloscopes to work with. But in the simulator, there's one built in, and so far seems to fit the bill. I haven't seen any issues with it yet, and pretty simple to jump into. So let's kick it off again. There are a few things that might trip you up when I was evaluating. I made note of that I wanted to make sure I brought up, so here they are. First of all, there are essentially two modes in this program. The first being a selection mode. Anytime the cursor looks like the traditional arrow, you're in selection mode, and that means you can move, drag, modify, change the specs on any components. Real simple. When you're actually putting down components and building your schematic, you're in draw mode, and that means your crosshair changes. It's going to be a little bit of an annoyance if you're trying to move something and you're accidentally drawing new components over your circuit. I'm only saying this because I was doing that while testing this and making sure it was doing a good enough job for you guys. So to get out of draw mode, which is what the crosshairs occupy your cursor, you just hit the escape key and that will put you back into selection mode. So that way you can move, modify, change things in your circuit as you're building it. Also, the delete key when you're in selection mode will remove remove a component, or you can drag and select several components and delete all of them at once. It's pretty standard stuff, right? In order to get into draw mode, you'll have to choose some components in which you would want to draw onto your circuit. And those are all done with the drop down menu at the top. You go draw, and what I really want you to familiarize yourself, because this is what we'll be playing around with the first couple weeks, is how to draw a wire, a basic connection between the circuit, resistors, which obviously add some friction to our electrons. Passive components, those are going to be things like capacitors and inputs and sources. Inputs and sources are how we're going to put a ground on our circuit if we need to later on, how we're going to put voltage sources, and how we would manually specify an amperage or a current in our circuit, in our simulated circuit. Also, something really cool about selection mode, anytime you double click on an existing component in your diagram, you can change the specifications and edit it right there on the fly. So I threw a couple examples of that. If you double click a resistor, it'll obviously allow you to change the resistance right there. It'll also put a label over there over the resistor telling you exactly what the resistance is set to. You can change the voltage coming out of the voltage source, which we would have gotten from our inputs and sources in the drop down menu. And then also something that's pretty cool is if you double click on a wire, you can actually click to show the current or show the voltage running through that specific section of the wire. So that will help you out when you're just trying to troubleshoot and take a look at how your circuit's working. I wanted you to know that's there because it's not exactly obvious from the documentation. And let's be honest, I don't expect you to go digging through the documentation anyway. All right. So here is an example of a quick parallel circuit that I ran in the simulator, and I want to point out a few things. This bottom section right here that I've called out, that's that information dialog on the bottom. It's going to be there all the time when you're running the circuit simulator. I want you to note a few things. This is where it's telling me I have two bad connections. It also tells me the time that I've been using this, the uptime of the circuit as I've been simulating it, and any additional warnings. These two bad connections, anytime you're not seeing what you expect to see, look here in this information dialog box. It's a surefire way to see if there's something that's pretty obvious that you can fix right away. Additionally, the simulator is pretty intelligent and it'll show the nodes that are not connected properly and they'll put them in red as opposed to them being just part of the circuit natively with this little green section right here. So that's how you can see it says two bad connections. Those are my bad connections right there. The green wire is the output from the voltage source. I'm using conventional electrical flow, so it's coming out of the positive side. And then as it's leaving the components of the circuit, getting ready to go back into the negative side and achieve that equilibrium, it turns gray. These little yellow squares right here, these actually simulate the electrons. And as we have more amperage or less resistance, you'll see that those speed up in the circuit. So that's that intuitive part. I want you to actually see what's going on within your circuitry as you're starting to build these and simulate them. We talked about the oscilloscope really briefly. Anytime that you right click on a section of wire, again, you can show the voltage and show the current. This is an example right here. It's showing 5 milliamps and 0 volts going through this wire. Also, simultaneously, if you do the same thing to a component, let's say a capacitor or a resistor, something else in the circuit, you have the option of bringing up the scope or an undocked version of the scope. The scope meaning the oscilloscope. And that is showing you the waveform, the actual, the visual representation of both the voltage in green and the current in yellow through a specific component. Viewing it in the scope will panel them at the bottom of the simulator for you. Viewing it in an undocked scope mode will actually put a little window right next to your component so you can see it in real time near the component that you're evaluating. Pretty helpful if you want to take a look at it really quickly and see what's going on in one specific area. If you want to evaluate it by comparing several different components, you might want to go in the docked version where it's at the bottom of the screen. But we'll go through that later on. All right, and then one last thing. In order to specify a current, the volume of electrons that are going through your circuit, you're going to need to add something from the inputs and sources. You're going to need to add a current source. From there, you can double click on it, modify it, and then you can force the simulation or the simulator to run a specific current within your circuit. So it's something that I wanted to bring up because that might be a little confusing if you're trying to evaluate a circuit with a known current and there's no way that's obvious on the onset that you can force the current into the circuit without adding the current source. So that's how you do it. You go to the draw menu, inputs and sources, drop it down to add current source, and you would just click and drag it into your circuit like you would any other component, and then you can modify the value there. Okay, all that to be said, I think it's time to play. I'm ready to get into it, and I hope you are too. I would like you to follow along with me because I have some specifications for a circuit that I think is pretty simple in concept, but instead of doing the math, we're going to let the simulator do the work for us. And this is how we can use this thing. So I want you to draw the following circuit in the simulator. I'm looking for a series circuit. It's going to have a DC voltage source of 10 volts and there will be 3 resistors in series. We'll call R1 10 ohms, R2 will be rated at 20 ohms, and R3 will have a value of 30 ohms. I want you to only use the information from the simulator. I don't want you to do the brain sweat and pull out a pen and paper to do the math. I want to find out what's the circuit's current. What's the current going through the circuit in amperes? And I also want to know the voltage drop for each resistor. So if you feel like you're ready to do it and you want to jump in and give it a try, pause the video and go for it. If not, if you want to follow along and we'll do it together, then just keep press and play. Here we go. All right. If you've chosen to follow along, this Choose Your Own Adventure is for you. Let's rock it out. We know we're going to look at a series circuit, a voltage of 10 volts, I believe, and then 3 resistors, all in series, 10 ohms, 20 ohms, and 30 ohms. We want to find the circuit's current, as well as the voltage drop against all of the resistors. Let's see how we do this. Follow along. All right, first thing we're going to do, we're going to go into the draw menu. Typically, I like to draw the components first and then do the connections after the fact. So I am going to do exactly that. We can do passive components. No, we're going to inputs and sources. We're looking at voltage source to terminal, right? We want to simulate a battery that has a positive and a negative terminal. And if you see, there's a little keyboard shortcut. So I'm going to go straight to that. And I'm going to hit the V key. And you can see that my cursor changed to a crosshair. I'm clicking and dragging. So we see that we have the two different sides of the terminal, the larger side being positive, and the negative side being the smaller portion of the terminal. Let's go ahead. I'm going to go draw and hit add resistor, or what I could do is hit the R key for resistors. That's a little shortcut hack for you. And then we're going to draw out three resistors. We're going to put these guys in line. Now we've got the makings of a decent circuit. What we need next to do is connect all these and make it a full loop. So I'm going to go draw and then add wire. I could alternatively just press the W key and you'll see that my cursor changed from an arrow to the crosshair. Again, to get out of draw mode and go back into selection mode, I could just hit the escape key. But draw mode is where I want to be, and I want to do it with a wire. So I'm pressing the W key. All right, I'm coming out of the positive terminal. I'm going to the first resistor. You see that the resistor is now lit up because it is connected and in series. I'm going to the next resistor, lit up as well. The third and final resistor, we're rocking and rolling. Now let's finish the loop. I'm going to go right to where I think is the bottom of the terminal, and I am going to click it. Did I do it? I don't know. All resistors are connected. The circuit is a full loop, and you can see our little electrons marching around the circuit. Um, Also, I'd like to throw this out there. If you are not a fan of conventional current motion and you want to see the actual flow of the electrons, you can go into options and uncheck conventional current motion, and you would see the electrons flowing around this direction. But I like to see the positive charge carrier, so I'm going to do it this way. It's my preference, but you can do it any way that you want to. All right, so we've set up our circuit, we've got our components, and now we have to edit the components to fit the specification. First thing being, we need our DC voltage source to be 10 volts. If I hover over the voltage source, if you look at the bottom, it shows currently there is a VD, a voltage drop at 5 volts at this specific this voltage source. Let me double click this. I want to change this component to be 10 volts. I want 10 volts of pressure pushing the electrons through our circuit. I'm going to click apply and go OK. I don't know if you noticed, but the charge carriers are now moving faster because there's more pressure going through them. But we're going to counteract that right now because we're also going to change the resistor values. I think R1 we want it to be, this is 10K, we're going to go 10. It should go zipping around pretty soon here because we're offering much less resistance. Let's see, R2, we are going to make this 20, apply that, and they're really booking now. And then R3, that's the last bastion of resistance that this circuit has. We're going to put it to 30, which is dropping it a ton, and these should be zipping. Let's see. Oh yeah. All right, so that's a little too fast for me. I don't want to get motion sickness in front of everybody. So I'm going to change the current speed down a little bit. All right. So we can still see the motion of the charge carriers. It's just not causing epilepsy in anybody viewing this video. All right, solid. So let's take a look at what we have here. Actually, before I do this, I want to change these back. I'm going to go 1K again, 1K, and we'll leave that last one at 10. And we'll move the current speed up. I want to demonstrate the power of the oscilloscope in being able to see exactly what we have going on when we can visualize the waveform. So I'm going to right click, I'm going to go view in scope, and you can see right here, this is a visual representation of the voltage As it peaks, it makes a square wave and it becomes a consistently higher voltage drop across this particular resistor. I'm going to do the same thing to the last two. As you can see, the voltage is much higher here. It's almost a full 5 volts there. And then we're going to do the last one right there. So now we have, if you hover over the oscilloscope, you can see that they're highlighting this specific component. So we've got R1, R2, and R3. Let's change our values back to what they should be. I'm going to go 20 ohms and apply. Again, I'm double clicking to edit the component. This is 30 ohms. There we go. All right, let's bring that current back down. All right, so what was our goal? Our goal was to figure out the current going through our system. Well, we're using a series circuit, and we know that the current is going to be the same going through all components in a series circuit. So let's pick any one of these sections of wire. I'm going to right click and I'm going to say edit, and I'm going to say show current. Let's take a look. 167 milliamps, and that is equivalent to 0.167 amps. That's accurate. That's exactly what we're looking at. So anywhere that I go on this particular circuit, it should show the exact same thing. Let's take a look. I'm going to show the current right here. That's it. All right. Next, we want to know the voltage drop across each one of these resistors. Let me really quickly do a spoiler alert and go to the answer page. Our current going across the entire circuit should be 0.167 amps, which it is, and we should have 1.67 volts, 3.33 volts, and 5 volts respectively across resistors 1, 2, and 3. Let's see if the simulator is doing us justice. If you can look at the bottom of the screen right here, it says there's that 1.666 repeating, so 1.67 milliamps of current going through the resistor, but also it says VD, voltage drop, being 1.67 volts, and the resistance being 10 ohms. Let's take a look and make sure that's right. 1.67 volts, that's 100% accurate. Let's take a look at resistor 2. That's showing 3.33 repeating volts. That's accurate. And our final one should be exactly 5 volts. Let's take a gander. Bottom right corner of the screen. VD is equal to 5 volts. I also want to point out something too. Look here in the oscilloscope reading. It's showing exactly what the voltage is. 5 volts on a 30 ohm resistor. 3.33 volts on a 20 ohm resistor, and 1.667 volts on a 10 ohm resistor. Check this out. This is also really important. This yellow line represents the current. 167 milliamps or 0.167 amps going through the circuit. This line is the same level on each resistor. I'd also like to demonstrate something else for you while I can. Since we're looking at these oscilloscopes, which are representations of the voltage going through each component, as I go down the line here, I want you to look at these lines, and it might be difficult. Let me, I'm going to reset these guys. This baseline right here represents 0 volts, right? That's the ground bias of the battery. But this represents the waveform, the visual representation of the voltage going through this resistor. If you look at these at these values here, 1.67 volts. Physically, if you're looking at it along the same scale, and these are slightly off scale, but it's lower than this, which is 3.33 volts, which is also lower than the 5 volts that we see here. So you're actually seeing a visual pictographic representation of what's going on in the circuit, and that's the power of having the oscilloscope and also being able to simulate these circuits to see what's going on. Uh, Ideally what we would see is, and you can kind of see it, the current, this yellow line, is the same going all the way across because the current is going to be consistently the same value through each component. This last one's a little funky because I messed with the scale to show a more drastic difference between 5 volts and 3.33 volts for you, but you can see it. So I think we've figured out exactly what we wanted to do, right? We've got our current through the system, 167 milliamps or 0.167 amps. That's consistent through each one of the components as we go through the line, even down the wires as well. We also can see that our voltages for each resistor is exactly what it should be, 0.167 volts, 3.33 volts, and 5 volts. This is exactly the answers that we get if we try to do it on paper or in a calculator, but we're having the simulator do the work for us, and we can visualize it on top of that. I hope you enjoyed this video, and I hope it made sense on why we want to start using the simulator to actually get a feel and see what's going on. And also we can construct these theoretical circuits that we've been talking about for a couple weeks now in the course and put them together and make some cool stuff. So I'd love to see what you're going to do, and stay tuned for an assignment where I'm going to have you experiment by making a series circuit, playing around with some of the values, and then we'll play around with a parallel circuit too. So continue to experiment, and I'll see you soon. Bye guys.